Hey, hello, and welcome here. We're going to go ahead and get started on our first and only modern physics lab here. And this one is the photoelectric effect. And hopefully you made sense to you. Let me review it real quickly, and then we'll do a lab on the photoelectric effect. Let me come over here. The photoelectric effect, as the name implies, or this is why it's called the photoelectric effect, is that the early scientists took different materials. It really doesn't matter what the material is. Let me just say we have some material and not even specify what it is. But then they were shining lights on it. And they tried different combinations of light, different frequencies, different intensities, and they noticed something interesting. And that is the electrons that are in the material get ejected under certain conditions. Excuse me. And so they measured all these conditions. And it was actually quite baffling to them. There were a couple things that did not make sense to them. For example, let's kind of pretend I'm the electron in this material. And as this light comes and hits me, the old way of thinking, okay, so before quantum mechanics, the early scientists would be saying, okay, this light is made of an electric field. The electric field puts a force on the electron. That makes sense, and that's going to interact with the electron. So the fact that the electrons get ejected isn't a surprise. What was a surprise to them is, if you kind of think about this, that there would be, let's say the light had a low intensity, and I'm the electron, the wave would push me one way, and then the other, and then the other. And each time it would push me, I would build up more energy, and then eventually I would break free. And so with that thinking, there should be a time delay for when these electrons get ejected. And there was not. Excuse me. Now, that didn't make any sense to them. Another thing, let's see, there were about 4 big ideas. Another idea, was that same idea that, okay, low intensity, it should then build up and eventually break them free. High intensity, that should really slosh them quick and break them free. So I already said there was no real time dependence as they kind of expected. But again, along those thinkings, you would expect that the ejected electron had more energy when you had more intensity. And again, that's not what they saw. They saw when you had more intensity, you had more electrons ejected, but the electrons that were ejected were all at the same energy. And again, that was just mind-boggling. They had no explanation to what they were observing. Another thing that made absolutely no sense to them is that as they changed the frequency of the light, that changed the kinetic energy that the electrons were being ejected. And again, that wasn't making any sense. If you're just thinking about these as being waves, then you expect the intensity to affect the kinetic energy of these ejected electrons. But it was the frequency that seemed to play the major role. And it just didn't make any sense to them. And along those same lines, the fourth thing was what they called a cutoff frequency. See, once they turned the light down to a low frequency, below some value, they called it the cutoff, then the electrons weren't ejected at all. And again, that didn't make sense to them. They said, well, they were thinking that if they're just being sloshed back and forth and eventually they would break free, it didn't really matter whether there was a high frequency and they would slosh and then break free. Now, that might do it in a shorter amount of time than at a low frequency where they'd slosh back and forth and then eventually break free. But there should not be a low cutoff frequency. Anyways, so those were the four main reasons, and I covered those in lectures, so maybe I shouldn't dwell too much time on this, but we do have a relatively short lab, and I just wanted to kind of review what was going on in their thinking, and this big part of their thinking was it made no sense. So in steps Einstein. And as a side note, this is eventually what Einstein gets the Nobel Prize for, although he could have got it for many other reasons too, but this is the actual Nobel Prize that the Nobel Prize Committee gave him the prize for. And he actually noticed that these four unexplained phenomenon could be explained with one idea. And therefore, that gave it a lot of strength. His logic was simply this, that we need to stop thinking about the light as being a wave and think of it as being a particle. And again, you heard me say that in the lecture. Today we call those photons. Now, Einstein didn't use the word photon, but he called it the quantum of light, or the quanta of light, and I'll just call it photons. So think about this for a moment. Let's change our thinking, and I'll maybe even draw a new picture here. So here's the material. Here's the electrons buried in the material. Here comes the light, but now I want you to think about the light not as being an electromagnetic wave, as we've been doing for some time, but to think of the light as coming in packages, kind of like you might say little particles. You might say kind of like shooting BBs at a metal surface. And Einstein realized that if they came in, if they had enough energy, and there's the key, if they had enough energy. Well, where do they get their energy? Well, remember, he's continuing on Planck's thinking, where Planck said that the energy would be hf, Planck's constant times the frequency. So Einstein is thinking that, look, if they have enough energy, when they hit them, they'll break it free. If they don't have enough energy, they won't break them free. And their energy depends upon their frequency. And hence, one of the biggest unexplained phenomenon gets explained, that there would be a cutoff frequency. That is, if the frequency is too low, it doesn't eject them. It doesn't matter what the intensity is, it just doesn't eject them. And so that totally changes the thinking of what should happen. And so that introduces an explanation for why there is a cutoff frequency. Why there is a point that if the frequency is too low, they will not get ejected. You got to have enough of it. Remember that first one I said, the time dependency? Same thing here. So as soon as these hit, if they have enough energy, they eject them. If they don't have enough energy, they don't eject them. So there is no time delay. There's no sloshing around, building up energy and breaking free. It's just as soon as they hit, boom, they eject them off. And so that explained the, I'll call it the second one. It's the first one I mentioned was a problem, but it is the explanation of why the time dependence works out the way it does. It also explains what I said earlier, that the dependent of how much kinetic energy these have depend upon the frequency. So you can kind of see, if these are thought of as particles and the particles have an energy that's based upon their frequency, that if the frequency is, and I'll say it again, below the cutoff, nothing happens. If they're above the cutoff, then they do eject them. And the higher the frequency is above the cutoff, so the higher this frequency is, the more kinetic energy it has to break them off. In fact, mathematically, Einstein would put it this way. It would be a conservation of energy argument. He would say, okay, so the energy coming in, hf of the photon, so there's the energy coming in, although we could write that as h, and instead of f, we could write it as the speed of light divided by its wavelength. Okay, so this is the energy coming in. Where does it go? Well, his argument is the first bit of energy has to break it free. That's the work function. And so different materials would have different values to break it free. Okay. And then anything that's left over then would be the kinetic energy of the electron. And so now you begin to see that the higher the frequency for that given material, the higher the kinetic energy. You can also then begin to see in this model that the intensity of light would then vary depending, the intensity of the light could be looked at as how many of these photons do you have. And so when they come in and they hit and knock the electrons free, what ends up happening when you have more intensity is you have more electrons being knocked free. The ones that get knocked free all have the same kinetic energy. And that was the beauty of his explanation. And so do you see how by thinking of these light as photons, as particles, this dual nature that I talked about in the lecture, we then can explain these four, I'll call them concerns, by the early scientists. These four pieces that the scientists could not explain are all explained, and I might even say simply explained, by just doing one thing. And so this is why Einstein said we are left here to accept the fact that we have to think about light as being quantized. This experiment illustrates it in four different ways. It's got to be quantized. And so that's when he introduces this whole idea that you've heard me joke in class, we call them the wavicles now. So they are thought of as sometimes waves, and so some experiments made sense when you think about them as waves. The Young's double slit that we did back in the optics only made sense when you think about them as waves. They don't make any sense when you think about them as particles. But other experiments demonstrate the particle nature of that, and that's what this one is. So what we're going to do today is really this experiment. We are going to shine light. We are going to actually have 5 different lights, and so 5 different frequencies, and we're going to then eject the electrons, and they're going to come out with a certain amount of kinetic energy. Now, we'll do one more thing. The way we will measure those kinetic energies is we will put a metal plate right here. And so these ejected electrons are headed towards this plate. We'll put a little counter here that's going to then say, okay, are there electrons coming? But we are going to hook up a power supply. Maybe I'll just put negative, negative, negative here. Because if we make this metal plate negative, then these electrons that are trying to get to this metal plate are being repelled by the negative charges on this plate. So will they get to the plate? Well, the answer would be say, it depends. It depends on how much charge you put on the plate. It's no different than throwing something up. I'll just take this marker. When I throw it up, it's being repelled, if you will, or really it's being pulled down by gravity, but it's having a hard time getting to the ceiling. Will it actually hit the ceiling? Well, it depends on how hard I throw it and the strength of gravity. So this, no, it doesn't hit the ceiling. This, yes, it does hit the ceiling. So do these electrons actually make it here? And the answer would be yes, if I didn't have much voltage here in combination with how much energy, kinetic energy, do they get, which is related to the frequency of those photons. And so what we're going to do then is measure what we will call the stopping voltage. How much voltage do you have to put on this plate so they stop being collected? They get blocked. And you'll see here, we'll kind of do it the other way around because our equipment is designed this way. We'll put this at a very high voltage at first, which basically would mean these electrons get ejected way early. They don't even get close. And then we will slowly turn down this stopping voltage. And when we first turn it down, they'll get a little closer. We won't be able to see them, so we won't know they're not any closer, but we will know we're not collecting anything. So we've got a little counter right here that's going to say, hey, are we collecting any? And it's going to say no, so we'll turn down the voltage a little bit more. And maybe at that point we're still not collecting them, but at some point we will turn this voltage down low enough that all of a sudden one or two will just make it, and our counter will go, and there'll be a little needle here. First be pointing at 0, and then it'll go up a little bit. And of course, if we turn it down, it goes up a lot. And so we're going to be looking for that magical spot where it goes from counting nothing to just something. Okay? And at that point, then, we know that this stopping voltage, and I should say stopping energy, is connected and equal to the kinetic energy of those coming. Back to my silly analogy of throwing this marker up at the ceiling. If it doesn't have enough kinetic energy here, it doesn't make it. It only gets to here. And right here, that potential energy that this marker has is equal to the kinetic energy it has down here. And so what we're going to do is hopefully get a perfect match that it goes up and it just barely touches the ceiling right there. And at that point, then, we could argue that we know what the kinetic energy is of the ejected electrons. We know that the kinetic energy is equal to the energy that were used to stop it. Okay, so what is the mathematical connection between the stopping voltage and energy? Well, here's where I'm going to have to throw a little formula at you guys from Physics 122. So half of you have seen this, half of you have not. Well, I guess all of you have seen it in the lecture. But the energy is the charge times that voltage. Since these are electrons, I'm going to put E for the charge of the electron. And then this V naught is what I will show you in the equipment. And this will be that stopping voltage. So this equation looks now like this. It has hc over the wavelength of the light coming in is then equal to the work function plus the charge of the electron times the stopping voltage. And what we're going to do here in a moment is make a little experiment, and we are then going to measure the wavelength and the stopping voltage. And as I said, we are going to start with a high voltage, and likewise we're going to start with a high energy photon. So we'll start over in the violet, and we will then see, if we do violet, maybe I better come all the way over here to this picture here. But if I start here with the violet, which will be our most energetic photons, they'll come in, they'll hit, and I believe our material is cesium, and it will eject them with a lot of kinetic energy. And so my stopping voltage will be kind of on the high side, okay? And I'll need that high voltage to stop those ejected electrons. Then we'll go to a little bit lower, which would be, let's see, Roy G. Biv, so blue. So we'll go down to blue. And I think then we'll do green, yellow, and red. Okay? In fact, let me put that in the little chart here. I'll just put here color. And let me open up the lab manual to page, well, I think it starts on 42. Yeah. But there is this little chart here that says, okay, what color? Now, our chart puts the highest energy photons down at the bottom, so I'll follow that pattern, but I'm gonna measure it then from the bottom up. So I'll do the violet first. Then I'll switch it over to the blue light. And they list the wavelengths. So the violet one has a wavelength of 400, and these would be units of nanometers. I'll switch over to the blue one, which will then be 464 nanometers. The third one will be a green. Our green one is at 525 nanometers. Then we'll do the yellow, which has a wavelength of about 593 nanometers. And finally, our fifth one will be our red one at 631. Okay. Now, all of these have enough energy, that is, they have a high enough frequency to eject our electrons out of cesium. So cesium has a pretty low cutoff frequency, and you have to get down into the infrared. So we're not going to see any of the, what I called earlier, the non-ejected electrons. All of these are going to actually be ejected. But the point is, you need some kind of minimum. In fact, I'll deviate a little bit from the experiment just to kind of show you this fun little experiment. But you can see this in action. We have here some tonic water and three different lasers. Maybe if I shine them on the board, let's see, which is this one. This is the green one. This one here is a stubborn one, but it's violet. And I have a red one. And just like the experiment we have here with the photoelectric effect, the photons in here all have slightly different amount of energies. And tonic water fluorescence, once it's hit with enough energy. So it has like a cutoff, if you will. So the red one, if I shine it through, you probably don't see much of anything. It's probably pretty boring. I don't even know if you can even see the red light off the surface as it just kind of goes into the tonic water and out the other side. It just goes right through the tonic water. And it doesn't do anything to the tonic water. It's below what we call its cutoff. Green one, I think this is the green one, yeah. Same thing. The green one, probably a little bit easier to see on the camera because it's brighter. But again, if I just shine it in here, you can see kind of a reflection off the surface. You can see it on my hand going through, and it just goes right through the tonic water. It doesn't do much of anything. The fun one to see is the violet. which has a stubborn switch. But as it goes through, it has enough energy to initiate the process of fluorescence. And let me not get involved in that right now, but you do see very different. You see the beam going through there, and those photons that get absorbed here in the violet then initiate the process and give it off. And you can see it even give it off a little different color. That's a blue instead of a violet, which is a whole nother interesting discussion in itself. But that's a good illustration of the cutoff frequency. And especially since in this experiment we can't actually do a cutoff. Well, we could, but that's not what we're trying to find out. So I'll say it again. These are the 5 different colors. These are the 5 different wavelengths. We're going to then measure what is the stopping voltage, because remember, the stopping voltage then is telling me the kinetic energy. But watch this equation here for a moment. Let me rearrange this equation. Let me do this. Let me put stopping voltage by itself, which of course I could get by taking the HC over lambda, subtracting the work function, then dividing by the charge of the electron. Let me rearrange it one more time. In fact, I'll just switch the order just so it looks a little nicer. So here is the stopping voltage. Here is the HC over E times 1 over lambda. So that's this term. And I'll explain this one in just a second. And then minus the work function over the charge of the electron. You will see wavelength in this equation. Okay, good. We've got wavelength. And you will see stopping potential, which is what we're about to find. And so our little experiment is we are going to then plot the stopping voltage on the y-axis, and we are going to plot the reciprocal of the wavelength on the x-axis. And then according to our theory, this should be a straight line where this is the slope. Now I know I haven't collected my data yet, but once we collect the data, this is where you guys are going to go to your graphical analysis, and you're going to make a new column. The new column is going to be 1 over the wavelength. And then you're going to make a graph. And that graph will have the stopping potential on the vertical axis. And that's why you need to make this calculated column. It's just 1 divided by this column. And you can put that right here, 1 over the wavelength. Now, I would suggest that maybe I should have thought about this ahead of time. Maybe we should enter these wavelengths in meters, because you're going to run into a little bit of trouble. So let me take away the nano, and then when you type it into graphical analysis, type it in as 631 E negative 9. 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 Okay? And so that's how graphical analysis will let you do really small numbers. Of course, there's other options too. So whatever you want, it's probably nice to have this in meters so that when we get this column that's the reciprocal, it'll be in inverse meters. Okay? And so over here, this would be units of inverse meters. Okay. But regardless of the units here, you hopefully then will see a straight line. That's what this theory is saying. Because again, the x-axis is 1 over the wavelength, and the y-axis is the stopping voltage. So you should see a line that has a slope of this and an intercept of this. So you will hopefully see something that looks like this. Okay? Because once you have made your graph, which I'll say it again, obviously you can't make the graph yet. I haven't helped you collect the data yet. Okay. But once you make this graph, do a linear curve fit, and as you know, the computer will tell you the slope. If you set the slope equal to HC over E, and you take your value of the slope, or maybe I should say our value of the slope, since we're doing this kind of online together. I collect the data, you analyze the data. But once you put it into this table and you get that slope, set it equal to here, because we know the speed of light is 3 times 10 to the 8th. And we know the charge of the electron is 1.602 times 10 to the negative 19. Or, if you don't know, let me tell you that it is, because this is more from Physics 122. I should put units up here, so this would be meters per second for the speed of light, and this would be coulombs for the charge of the electron. But here is your final step. What is the value of Planck's constant according to our data? Now, you know from the lecture it's 6.63 times 10 to the negative 34 joule times second. And so hopefully that's what you'll get something close to. Now let me emphasize, this is a really small number. So if you get anything that says times 10 to the negative 34, we'll take it as we did a good job. Okay? So don't worry about this beginning part. If it said 4 times 10 to the minus 34, hey, we're doing well. Just the fact that we could find it to the, what we call order of magnitude, we're going to be happy. Okay? And so that's the ultimate step here. So I'll say it again, right? It's the photoelectric effect. We're going to collect some data. We're going to find this stopping voltage, and I'll write that in here in just a second. But once we find all these, then we can make this graph. We can get the slope, and the ultimate step from the slope is to figure out what is Planck's constant. And that's what you're eventually going to be turning in. I think there's a couple of questions, but that is question actually number 3. Of your 3 questions, question number 3 says, report your experimental value of Planck's constant. And that's what they mean here is take your data, get a slope, find out what you get for Planck's constant. And by the way, as long as I'm talking about the questions, look at question number 1. Question number 1 says, derive the working equation used to determine Planck's constant. So they want you to just kind of do this logic that I did over here, is that, hey, start with the energy in equals the energy out, rearrange it, and you get this formula. So this is the formula that they want you to get. And so you can basically just run through that. I don't want to say copy. You should really understand and run through it, but that's what they want. So I have it there on the board for you. Now, again, as long as I'm on the questions, let me do the last one here, because question number 2 is a question that really has to do with our old equipment. See, question number 2 says, what if you had multiple wavelengths at the same time? And we kind of do, we just didn't give it to you that way. See, what if this blue light wasn't just 464 nanometers? Or what if the blue light had a range? And it really does. Now, this one says it with filters, because the old equipment we had filters, but the question still applies with the equipment we have today. It just needs to be changed and updated. And so that's what I want to do here. This blue light really has a range of 464 to about 484. And so there's a range of frequencies. And this question is saying, okay, if you have a range of frequencies and you run this experiment, what should you do? Should you use the smallest wavelength? Should you use the biggest wavelength? Should you use the average of the wavelength? What should you do? Now, you can see that I gave you the smallest one. And so that kind of answers the question. You want the smallest one. But why? Why do you want the smallest one? And if you come back over to here, you can see that if you had a range of different wavelengths, that would give you a range of different kinetic energies. And if we're going to adjust our equipment so we just begin to see them, then the highest energy ones are the ones that are going to hit here first. And the highest energy ones are the ones that have the smallest wavelength. And so that's why you'll see when I actually begin to run this experiment, I will start with the voltage, what I'll call too high. And it will stop all of them. And as I lower it down, I'll first start collecting, and then the needle will move up just a little bit. And what that tells me is the highest energy ones are just making it. And the highest energy ones are the ones that are getting hit with blue photons that have a wavelength of 464 nanometers. So that's why in our chart, it has already been picked for you that these are all the smallest wavelengths, because these are the highest energy photons. All right, well, I didn't mean to get into the questions before actually running the experiment. Usually I like to do the experiment and then come back to the questions. But now we can actually get the data for you. So bear with me, we won't be long now, but let's collect the 5 pieces of data, and then you can go to graphical analysis and do this and do your slope and get a number, get a calculation, and answer those 3 questions, including the big question number 3. What is your experimental value of Planck's constant? All right, so let's go ahead and actually get the data here. All right, so collecting the data is pretty simple, because what I did not tell you, and I will turn this off and pull off the cover so you can kind of see what's going on under the cover here, is that for all of this to work, there's a bunch of integrated electronics and vacuums that mean we have to have pre-done equipment. Oh, watch, let me come back over to here. Remember when I talked about these ejected electrons that are coming over to this collecting plate? Well, this all has to be evacuated. Maybe I'll put a box around it, but all of this needs to be free of other molecules. And so in here we have then our vacuum, and so this is our cesium. And then this is the vacuum to the collection plate. And if you look at our little window, there is a glass window, and behind that there's kind of a bowl shape. That's the cesium, and then there's a metal piece out in front. And the reason the window is here is so that I can shine the light through the window. So if I come back over here to this picture, here's what I'm going to do is I'm going to send the light in through the window. It's going to hit the cesium, it's going to bounce or get absorbed and eject the electrons, and then it's going to go to that collecting plate, and then that collecting plate has a built-in or an integrated adjustment knob that I can get the voltage. And so you can kind of see the equipment better. I'll pick it up and turn it around. But that big knob right there is the stopping voltage. It even says voltage adjustment. And this is the on and off, and this is the zero calibration. So what I'll do is I will turn it on so you can kind of see the adjustment. Whoops. And I want to turn it on with the cover here on it. And the zero adjusts is for this is the counter, and I'll move it a little bit and you'll see that it changes this location. So what I want to do is just adjust my counter. See, right now I have no light coming in. That's why this cover is on here. I also have the stopping voltage turned all the way down. And so I just want to adjust this, and I want to do it while it's stationary. So I'm going to put it down now. And I'm just going to adjust it until it says 0. All right. So it says 0. So the counter says 0 when it's getting bombarded with 0 light. And of course, the voltage, stopping voltage is 0 also. Okay, let me turn it off and take the cover off, because if I were to take it off with it on, the cover off while the equipment's on, it just gets blasted with room light, and the counter goes so far over I could damage the counter. So okay, I'm going to turn that off. And I'm going to go ahead and turn up the stopping voltage. To some value that I just know is too high. I just know by turning it halfway that's too high. And let's just go through these colors. So I'm going to start with my violet light. This is a little LED light. This is the glass end of the light. This end over here has the electrodes. In fact, you can even see if I hook on my power supply. So I've got a little 4-volt power supply right here. And if I turn this on, ta-da, I get violet light. Okay? And so that's the one I'm going to hook up first. I'm going to put it right in front of the window here so that the only thing going in is this violet light. There we go. And you can even see it blasting in there, if you will. And now I'll turn it on. Now, when I turn it on, hopefully the counter does a little bit of nothing. Whoa. Because I want to find right where the counter starts to jump. Okay? And try to get some decent data. And that was going up just a little bit. And so I'm going to call that good and say for this violet light, I'm getting a stopping voltage of about 0.781 volts. Okay, so with that in mind, I will turn it off, and we will go to the next light, which I said was blue, and we will blast blue light in here. Here's a blue one. Maybe I'll even show you this one also before I connect it all the way on. But if I hook up the blue light, ta-da! There's the blue one coming at you. So I will put the blue light here. Okay, and then I will turn it back on. And of course, no electrons are able to make it because, of course, they are at a lower energy because they're getting hit with photons that are blue. And let's call that good at 0.724. So 0.724. So you can see they have less energy. Took less of a stopping voltage to stop them. Okay, we'll continue on. Turn this one off. Go from blue then to green. And I'll just put the green light in the window. I didn't show you the green one this time, but hopefully from the back side of the LED you can see the green light come on. Oh, no. Might have got the electrodes backwards. Let's try this. Ah, there we go. I did. Sometimes it's hard to tell which wire is longer, but if you guys were in class, I'd tell you the long wire is the positive one, and it's only a fraction longer, and so when they flare out this way, it's hard to tell. But anyways, there you can see the green light shining in. So I'm going to turn it back on and look at my counter. Okay, and my counter is clearly showing me that they're being ejected or they're being pushed away. It goes down the negative side. So I'm going to turn this down a little bit. Turn down the voltage even more. Oh, right there. Okay. Now I'm going to look at my little counter. Maybe give it a chance to stabilize. But it looks like 0.563. 0.563 volts. So again, a little lower. Okay. So I'm going to turn this off. And now, lower energy photons. Let's go to the yellow lights. This one looks a little longer. This one maybe I will just show you just to make sure I got the right electrode. Ah, yeah. So there's the yellow one. Okay. Okay. Let me put the yellow light in the window. And same idea, blast it with photons that are in the yellow range here, 500 and what do we say, 25. Okay, and so you can see the yellow one, so I'll turn it back on. But again, the stopping voltage is way up here, so it's pushing them away. They're not getting to the collector. My counter notices that and goes negative here. So I'm going to turn down the stopping voltage. Down, 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 down. Ooh, starting to move. Okay, right there. Nice. All right, and so that took less stopping voltage. So this is 358. So 0.358. All right. And by the way, you can kind of see where the cutoff voltage would, or the cutoff wavelength would be here if we plotted this down. And you will. We're not asked to do that. That might be a good fourth question to ask. All right, and then the last one here. Let me turn this off and get rid of the yellow light. There's yellow. And the final one is the red one. And this one looks a little bit longer than this one. Yay. Okay, so here is the red. You know, it looks kind of a red orange to me. What is this one? Yeah, because it's 631, which those Heaney lasers we keep using in class for the interferometer. Those were 632, and they're kind of on that borderline of red and orange, depending. Of course, everybody's eyes are a little different. That's why we like to, in a science class, not talk about its color too much. Just, you know, what is its wavelength? Because what somebody calls orange, somebody else calls red, and it's a little confusing. Anyway, so this is kind of a red-orange to me, but our book calls it red. So 631, let me turn this on again, and sure enough, stopping voltage is too much, so let me turn it down. Turn it down, turn it down. Oh, right about there, looking good. And, my voltmeter went to sleep on me. Okay, let me turn it back on. So that's still good. And then this is 258. So 258, or 0.258 volts. All right, so that's it. That's the data. That's, I guess, my half of the experiment is where I work with you, kind of showing you the equipment and then getting the data. But I'll say it again, your job now is to take this data and to put it into graphical analysis. Make sure you calculate a new column here. Watch your units, and then get this graph, and then get this slope, and then get this h, which is the answer to, or Planck's constant, which is the answer to question number 3. And of course, we've already answered 1 and 2 together, but go ahead and write that out and put it all together, turn it in on Canvas. All right. You guys have a good one. Take care.